Yeah, depending upon the amount of redundancy present in a database design, we can have different normal forms. So in the last session, we have seen regarding uh, fourth normal form, fifth normal form, and also we have seen some other type of dependencies. And I was telling you that normally the dependencies between two different attributes can be straight away, expressed using the concepts of FD and what do you call it? MVD. But and also we have seen that joint dependency is actually a generalization of FD and MVD. And we have seen that still there are many other constraints or many other meanings which we cannot express using this concept of FD, MVD, and JD. So for that, we have noticed that there are many other dependencies defined in the database context. So what are, can you give an example of a dependency which cannot be expressed using FD or MVD? Agnijit. Agnijit is present. Present here. Devendra.
Yes, sir.
Can you, yeah, give one example.
To show that it is MVC, so multi-valued dependency.
No, I mean an example of a case where the dependency cannot be expressed using FD or MVD or JD.
I think the key when all the attributes are act as a key, then we can say.
I'm asking about any specific example of some case where we cannot express the dependency or we express the meaning using the three different functional dependencies, which are the formal mechanisms by which we can express formal mechanisms for expressing the meaning of data.
Yes, sir. I'm saying that when all the attributes act as a primary key, and a primary key is functionally dependent on itself, sir. Then in that way, we cannot get any information regarding the table because all the attributes act as a primary key.
Okay. So, Santosh Kumar. Santosh, can you give any example for a case? Santosh is absent. Sarita.
Sir, tuple generating dependency.
Yeah, give an example.
Sir, in case of a scholarship, there is some condition that only for females and they are from certain two states.
Okay. Yeah, Damira, can you make it little more clear? Sarita has given a example.
Yes, sir. I believe you kind of give an example where, say that a student can be given some kind of scholarship based on his grades in the number of subjects, like if there are more than 5 or something. So based on that, it is kind of not dependent on the data, and we are not storing that. So that is very difficult to show it in terms of functional dependencies.
Okay. Yeah, there is a table which is called scholarships table, or there is another relation which is called gold medal winners, where you have to get tuples where the CGPA is the highest. So that cannot be expressed. I mean, the thing is that if you have a tuple in the gold medal table or gold winners or gold medal winners table, and if the tuple is not present in any of the other student table, then we say it is wrong. So that cannot be expressed using FT, JD, etc. So for that you require another kind of dependency. We have seen about that. They are tuple generating dependencies, and there are many such new dependencies. And also we have seen regarding domain key normal form, where we insist on certain domain for the values coming in a particular field. So can you just quickly recollect the example that we were discussing? Hello. Hello, Laushe. Hello.
Yeah, hello, sir.
Yeah. So can you give an example for that? DK domain key normal form or domain constraints? You were present in the last class?
No, I was absent.
Okay, then of course you won't be. But did you see the video recording?
Yeah, I've seen.
Hmm. Anakha?
Hello, sir.
Yeah.
Sir, the roll number where the M stands for MTech and 21 stands for the academic year, CS stands for the department.
Okay. So how it becomes a domain constraint? What you have said is correct, Anakha, but can you just relate it to the domain constraints or domain dependency?
Sir, they are dependent to other tables.
Yeah, not that. So the first letter or the first thing coming in your roll number should be from the set M, B, P. That means M for MTech, B for BTech, and P for PhD. It cannot be K or L or Y or Z or anything. All right. So there is a domain associated with the there is a fixed domain associated with the first position. Similarly, the second two positions, it should range from 00 to 99, isn't it? You cannot have something, I mean, a minus value. Say, I cannot say that M minus 2 minus 2 like that, because it should be a positive integer and it should be from 00 to 99, between that. All right. Similarly, the last two characters should be either CS or EC or ME or CE. So there is a fixed set defined. So you cannot go beyond that particular domain. So that is actually the domain normal forms. I mean, that is actually the domain constraint. So that is also not, that meaning also, or such meanings cannot be expressed using the conventional ways of expressing the meaning or semantics of data. That is this FD, MBD, and JD. All right. So we close the discussions on normalization there, but even though we haven't done any exercises in the class, so the question that you can expect from that portion is, given a set of tables, you will be, or you should be ready to normalize the table into a specific normal form, or you may be asked to find out in which normal form a given set of tables is and what is the reason, give justification for that, or you will be given a set of tables and you will be asked to normalize it into 4NF or like that. All right. And also be ready, you should read more about closure set of functional dependencies, derived FDs, etc. Okay. So we did not do such exercises in the class. That doesn't mean that you need not study those things. So I expect all of you to be thorough with all such practical problems. So any questions on that before we move on to the new topic, normalization? So it is considered to be a very important topic in database context. That's why we spend 2 weeks on revising normalization concepts. Yes.
Sir, can you explain little more about the fifth normal form, sir?
Which normal form?
Fifth normal form, sir.
Fifth normal form.
Yes, sir.
So what we have seen in till 4NF is that the method adopted is to divide a table exactly into 2 subtables. All right. So, and so that when you take a natural join of those 2 tables, you will get the original, all the tuples and all the functional dependencies in the original table back by taking the join. But there are certain cases where you will not be able to decompose a table exactly into 2 subtables, but you may be able to decompose it into 2, more than 2, that is 3 or 4. That means if I decompose the table into 2, I will be losing some functional dependencies, or I may be losing some tuples in the parent table. So till 4NF, you go for dividing it exactly into 2 subtables. But in the case of 5th NF, you divide it into more than 2. So if I have a table with the column A, B, C, D, maybe I divide it into AB, R1, AB, R2, BC, R3, BD. All right, AB, BC, BD. So I say that they satisfy the joint dependency of AB, BC, and AD. So I take the join of these 3, I get the original table ABCD back, and there all the tuples will be regenerated, and all the FDs will also be regenerated. So is it that that is actually the difference? Maybe if you want further, we can have an example, a real example later, maybe in the next class. You can just show that if you divide the table into 2, you are losing something. And if you divide it into 3, there is no loss. Is it okay, Suraj?
Yes, sir. Yes, sir. It's okay. It's okay, sir.
Okay. So the first and foremost difference is that there is a limit to which we can divide a table exactly into 2 in a non-loss fashion. So when that possibility fails, we go for joint dependency, where you divide it into more than 2. All right. Now we go to another important topic that is regarding the join operator and the semi-join operator. So join is a very important, and we have already seen towards the end of the discussions on normalization that if you go for normalizing the table beyond a point, maybe Probably if it is beyond BCNF or beyond 3NF, you will come across a collection of small tables. There can be a situation where you have a large number of smaller tables. So when you want to answer a query, you have to take the join of all these tables. So if they, especially in the context where all these tables are stored in different places of a network, it will be very, very costly because it involves a lot of communication of data from one location of the network or one location of the distributed database to another node. So in that case, we will see the reverse of the whole concept. That is, the optimizing parameter will be to reduce the amount of data transfer that is occurring. All right. So these are all, both normalization as well as these distributed databases are basically looking for some optimization problems. So we know that in most of the most of the problems that we find in IT, information technology, or in computer science are actually the optimization problems. So what do you mean by an optimization problem, Agnijit? You are back.
Audible?
Yes, you are
Hello?
audible. Yeah.
Yes, sir.
Unlike last time, you are audible now.
Yes, sir. Last year, it was a network problem. I was talking actually.
Yeah.
Actually, last time I was also talking, so it was a network problem.
What is the network problem?
I said last day, sir. Last to last day, I had a network problem. I was talking actually.
All right. Okay. You can answer the question.
Sir, I did not join the last classes, so I don't know.
Sorry, Agnijit, I did not
Actually,
hear.
I didn't join the last class, sir, actually.
Okay. Yeah. So what is actually an optimization problem means? That is the question. That was not actually discussed in the last class. I'm asking now.
Sir, I have no idea, sir. I don't know.
I'm saying that most of the problems that we come across in IT, information technology, which is actually an application of CS, computer science, there you find that most of the problems are optimization problems. Can anyone say comment on that?
Yes, sir. Can I, sir?
Yes.
Sir, when we want to maximize or minimize something, that problem belongs to optimization problem.
Optimization problem. Very good. So in the case of normalization, you are trying to minimize redundancy. All right. So it is an optimization problem. In the case of distributed databases, you are trying to minimize the communication cost. So it is again an optimization problem. So in general, in databases, you are trying to maximize. No, there also you are trying to minimize. That is a query processing time. So you should, given a query, we should be able to give the answer as quickly as possible. So everywhere you try to optimize the efficiency, or you may try to optimize the throughput, or you may try to maximize what you call the output, or you try to minimize the error. So people are not happy with the amount of minimization, or the level of maximization that you reach. You want it to make a little more. So that is why there are a lot of plenty of optimization problems in information technology. Or people are trying to apply IT or information technology on problems where you want to optimize some parameter. So here what I am saying is, in the case of join, or in the case of distributed databases, we try to minimize, or the optimization parameter is basically the amount of tuples which are transferred from one node of the network to another node. So first we will have a quick review of relational algebra, right? So, yeah, we know that in the database management system architecture, we have something called an SQL engine, right? So an SQL query will be converted into a relational algebra plan. So there is a query translator, or there is an SQL interpreter which will translate a given SQL query into an equivalent relational algebra expression. All right. Then this relational algebra plan will again be optimized, and you will get an optimized query. All right. So here again comes the optimization word, or the word optimization. Can anyone say what actually we do from the second part, that is from relational algebra plan to optimized plan?
So here we figure out how to execute the query with the least amount of resources.
Vishal?
Will be time out of the processing.
Other. Yeah. Louder, please. Other.
Yes, sir. I was saying in this step we try to figure out the way to minimize the time required for processing, or the least number of computations required to get to the data.
All right. So a carelessly written of a relational algebraic query may consume lot of memory during execution of the query. So one parameter is reduce the memory usage during the query evaluation. Another parameter, of course, will be regarding the transfer of data, or the amount of joins, or how the different tables are affected, or how much communication is involving during the query evaluation. So query optimization is a parameter which is there. I mean, it is a topic which is still having a lot of getting research attention. We'll study that in one of the coming classes. So optimizing a given query with respect to memory utilization, with respect to communication, etc. Anyway, in the DBMS architecture, after translating a SQL query into relational algebra, that will be optimized, and finally execute each operator of the relational query, or execute each operator of the plan for query values. So that is what is happening. Now, if you look into this, we have relational algebra, RA, which is actually a formal mechanism for creating new relations with existing ones. Okay. Here is actually the big picture where it shows the position of relational algebra. So we have something called declarative query languages. All right. And relational algebra is one among that. It is an example for a declarative query language, and it will be implemented, or so that will be really implemented using, I mean, query translators or interpreters inside the DBMS architecture. So we can have SQL, relational calculus, etc. as declarative query languages, then that will be translated into relational algebra or relational bag algebra, bag of relational bag algebra, and that will be implemented later. So these relational algebraic expressions can be simple or they can be very complex, as shown in this particular diagram. So here you can see a very complex relational algebraic expression involving three different tables: person, purchase, and product. But in this query, the table person is coming twice, appearing twice. So here you can see that first you are taking a join of purchase and person based on a condition that seller's SSN, social security number, should be equal to SSN from product table. All right. And from this product table, you are, or from the person table, you are taking the name and you are taking the SSN, and you are taking the join of that with the purchase table, and then parallelly you are doing some other selection and projection, and then again you are taking a join here, and then finally you are joining with the person table with the condition of buyer SSN equal to SSN from the right part, and then finally you are projecting the name. So here you are getting the names of persons or the buyers with certain conditions. So this query is apparently a very complicated one, where you have three different joins and two selections and three different projections. So such query evaluations are going to take too much of time, and as well as it will take huge amount of memory, right? Yeah, going for a quick revision of relational algebra, let us recollect that there are 5 fundamental operators in relational algebra. They are union, difference, selection, projection, and Cartesian product. So the symbols are shown here. So union, difference, and Cartesian product are binary operators, whereas selection and projection are unary operators. All right. Apart from these 5, we have many other derived or auxiliary operators. So intersection, complement, join. So there are different forms of join which we are going to discuss or revise today. That is natural join, eq join, theta join, semi join, and you also have outer join, left outer join, right outer join, and full join, etc. So they are all examples of various forms of join, and they are all falling under the category of derived operators in relational algebra. And you have one more operator which is called the renaming operator. All right. So we are going to have a quick review of these operators, and basically our focus is on the posterior operator, which is actually our join. All right. So here we know that union is a binary operator. You take the union of two tables. So you have a table of employees and you have a table of retired employees. So when you take the union of these two, you get the full list, and you have the difference also, minus R1 minus R2, all employees minus retired employees will give you the current set of employees. And intersection, as you know, it is actually a derived operator. It is actually called a derived operator because we can express it in terms of the fundamental operators. So R1 intersection R2 is actually equal to R1 minus R2. First, you take the tuples of all tuples which are in R1 but not present in R2. Okay. So R1 minus R2 present in R1 but not in R2. Then subtract that from R1. So what you get is actually the set of all tuples which are present both in R1 and R2. So this is an important expression. That means a difference operation. I mean, intersection can be expressed in terms of difference. Similarly, the other operators like join can also be expressed. Join is also a derived operator which can be expressed with an equivalent relational algebraic expression containing only the fundamental operators. All right. Now, selection is a union operator. As you know, it returns all tuples which satisfy a given condition theta. So here you just see that theta CR. So C is a condition. So theta on selection is applied to R, and those tuples which satisfy the condition will be listed. So two examples are given. Select salary greater than 40,000 from employee, or select all names. Select the tuple corresponding to the employee name Smith. All right. So the condition can involve relational relational expressions like equal to, less than, equal to, greater than, and all such combinations, not equal to and all. So selection is a union operator and it is applied to a single table, and the result is also a table where the arity or the number of columns are same as that of the table R. So an example is given here, same example, that is get the all tuples from employee where the salary drawn is greater than 40,000. So here you have Smith and Fred drawing salary more than 40,000. So this is actually the resulting relation or the output relation of this particular query. Similarly, we have projection. So in projection, it eliminates columns, then removes duplicates. That is very important. In the case of projection, we will not have duplicate columns, duplicate rows. The same tuple will not appear more than once. So that is very important that you have to note in the case of the projection operator. In a projected table, we will not be having duplicate tuples. All right. So the notation is pi A1 to AN from R, where A1, AN are all columns of relation R. So here you can just see an example where you are projecting the social security number and name of employees. So, so output is going to be a table with two columns. SSN first and name second. So it is shown here. So you are projecting two columns. So how these selection and how this projection operator is implemented in SQL, Chedana? How this projection operator is expressed in SQL?
Sir, using the select keyword.
Okay, so it is like quite interesting to note that actually the projection operator is implemented using the select keyword. All right. Now, how the selection is happening in the, or how it is expressed in SQL? Divyanshu Verma. Which keyword of SQL is normally, or we can correlate with the selection operator of relation?
I think unique, distinct tuples. Unique, I think.
Yeah, I was trying to correlate it with the where clause, WHER. Select some columns from tables where condition. So there actually the condition is the theta that you find in the selection.
Yes, sir. Where condition?
Yeah, this is actually coming as where salary greater than 40,000. The
Yes,
SQL. Yeah, I was just trying to correlate between these two. Now, Cartesian product is a binary operator, which is a posterior one. So here we know that R1 cross R2 will have all the tuples of R1 and R1 into R2. If you have 200 tuples in R1 and if you have 100 tuples in R2, so you will have how many tuples in R1 cross R2?
Sir, M cross N.
20,000 tuples. All right. And the number of columns will be the sum of the columns in R1 and R2. So it is going to be a very big table, which is coming when you take Cartesian product. So in general, Cartesian product also takes more memory. So it is employee and dependents. You use basically it for along with the join operator. Nobody will be stopping the stopping by taking the Cartesian product. It is actually an operator which is coming just before the join operators. All right. So Cartesian product. So two examples are given here. So you have 6 tuples, or sorry, 5 tuples. No, 4 tuples here. John, Tony, and their employee number and B name. So here comes the Cartesian product where you have name SSN, employee SSN, and B name, 4 columns, and you get 2 into 2, 4 different tuples in the resulting. All right. So there are 5 fundamental operators. We have seen that. Then there are derived operators called intersection, complement, and various forms of join called natural join, eq join, theta join, and semi join. And you have an operator called renaming also. So what is this renaming operator? This only changes the schema. That means you use this rename operator to provide more meaningful or more names which we can remember easily. So the database designer might have taken it as SSN num, SSN hash, or he will say buyer ID hash, etc. You can give probably a better name while you are generating the report. For that you use this renaming operator of relational algebra. For example, here, so rename last name and social security number from employee. So output will be a table with 2 different columns, headings. The headings will be last name and SOC number, social security number. So that will be giving more understandability for the table. So it does not have much significance or importance other than for making a table more meaningful or more understandable for the user friendly. Now coming to natural join, we have already seen that it is playing a very important role in relational query processing. All right, and it uses Cartesian product as a pre-step before taking the join. So when you take natural join, say R1 cross R2, so what you are doing is you are actually taking the Cartesian product of R1 and R2 based on a condition and then projecting few columns. So this is actually the equivalent expression for natural join of 2 different columns, 2 different tables R1 and R2. So first you take the Cartesian product. So in this relational algebraic expression, the expression which is coming in the innermost parentheses is executed first. So here first thing that is happening is the Cartesian product of R1 and R2. Then there the condition of conditional selection. Applying the condition C on that Cartesian product is applied, and then you project column A. All right, so this is an example. So when you are taking join, actually you are having 3 different operators. First, a Cartesian product, and second is actually the selection, and then there comes the projection. All right. So here, selection C checks equality of all common attributes. Maybe equality you are checking for some attributes. All right. Or the projection eliminates the duplicate column common attributes. So when you are projecting, you will not be having duplicate values in the table, in the column. So look at this particular example and convince yourself regarding the resulting table. The tables shown here are correct, is correct. Just look at that, look at the example displayed on the screen. So the resulting table is having 3 columns, SSN and BC, department name, dependent name, SSN, social security number of dependents, and dependent name. So this is an example of a natural drawing. So here again, there is another example where you have 2 tables R and S. So R, I mean, S is shown just before the table R, but take S as the second table, which is containing the tuples BC, ZU, VW, and ZV, and R is the first table. All right. So the columns are AB, named as AB in R, and BC in S. When you take the join, natural join, what you get is ABC. All right. So here you are trying to look for equality on the common column. Equality for the values which are coming in the column, common column. So you have XY, the value coming in the common column is Y, and none of the tuples in the second table S are having Y. So we don't have XYU or XYW or XYV coming here. All right. But if you look at the second row, XZ, we have ZU, we have ZV. So in the resulting table, we have XZU and XZV. Now you take YZ, you have ZU and ZV. So we have YZU and YZV in the resulting table. Similarly, when you take ZV, you have ZVW, VW coming here. So we have ZVW. Now read more about these natural join and give answers for the last 2 questions. Look at the tables and answer the last 2 questions. Read carefully the first point. Yeah, so now comes the question to Navneet. So given R, ABC and SD, what is R natural join is? If R is ABC and S is DE, what is R natural join? Yes.
Sir, there is no common column at no common attribute.
So what will be the result?
Sir, any 2 attributes should have same name. So here,
It is not there.
sir, we will get ABCDE.
ABCDE. Everyone agree with the answer given by Navini?
Sir, I think we'll get empty table, we'll not get anything.
Okay, so you will get a null relation or an empty table. That is what Piyush is saying. Any other opinion?
Tarun, sir.
Tarun, okay, Tarun is saying. Any other
Cartesian product.
Cartesian model? Okay.
Cartesian
Here,
product, normal.
Cartesian product of R, A, B, C. R and S, not null relation. So what will be the end result? Avinash is saying null. Okay, find out that. Then the second, yeah, other is also saying null. Chedana is saying cross product. Vishal is saying null. Okay. Yeah, find out what is the correct result. Agnijit is also saying null. All right. Yeah, now given two tables R, A, B, second question, there is a common column B, then what is our process? Let us go to Vikram. Vikram Deepak.
Yes, sir.
What is the result of, answer for the second query? R is AB and S is having two columns AB. All right. So what will be R join S?
Same AB, I guess.
Same table.
Yes, AB, because both the columns or attributes are common.
Okay. So how many of you disagree with him? Megha? Do you agree with what he has told? Vikram has told?
No, sir. It will be null, sir.
It will be null.
Yes, I think so.
Okay. Piyush, Abhishek, what is your opinion?
Sir, it should be AB only, sir. Any one table. There should be ambiguity, sir. Whether R should be taken as a table or S.
Okay. I think there was another response. If S1,
Yes, sir.
what is your opinion about the second query? What do you say?
Sir, I'm not sure, but I think it would be either R or S, any one of the two.
Okay, Rahul Moharana is saying ambiguity and intersection. That is what Yukta is saying. Intersection, there is, you have only, the same tuples, isn't it? Okay, intersection of R and S. Okay, common tuples. You have two tables, R, A, B, and S, A, B. The columns are the same, but the tuples can be different. Now let us hear from Rahul Soni. Rahul. Not person. Sahil.
Yes, sir.
Yeah.
Sir, in the third query, the join will be performed on R and S with the one of the columns, like with A or either with B, and both the columns will be present in the output A and B.
In the case of natural join, you should have all the tuples where the common columns have the same value.
Yes, sir.
So what will be the output? Here you have two tables R and S where the columns are the same. AB, AB.
Sir, I think in any one of the columns will be used to identify the common values.
It is not clear, but I am leaving to you to find out what is the answer for this when you are taking join of two tables where exactly the column, all the columns are the same. How many columns will be there in the resulting table and how many rows will be there in the resulting table? Someone was saying that it is intersection of R and S. Let us please find out what exactly the answer to that. I'm not giving the answer at this point. Okay, you can find it out. Now, theta join is another variation of join operator where you apply a condition theta on the Cartesian join. So R1 theta join R2. So first you take the Cartesian product of R1 and R2, then apply the condition theta on. All right. Now, EQ join is another variation of the join operator where the condition theta is actually equality. Okay, taking the Cartesian product of R1 and R2 and selecting some tuples based on the equality condition, then you call that form of join as EQ join. So EQ join is practically the theta join operator, theta join with the theta is equal to. That means the theta can be less than, greater than, less than or equal to, greater than, equal to, etc. So if you are having the symbol equal to coming in place of theta, you call it as EQ join, right? So here you can just see that R1 and R2 are applied with the theta join with the condition that for the value coming in column A of R should be equal to the column B value coming in the column B of relation R2. So it is very useful in this EQ join is very much useful in query processing, or it is a very frequently occurring operator in relational query processing. Now here comes a very important operator or a variation of the join which is widely used in distributed databases, which is actually called semi-join, half join. So here, this is you are taking the join of R and S. First, what you do is project few columns you take the join, and normally when you take the join, you take the Cartesian product of R and S and then project few columns. So where A1 to AN are the attributes in relation R. So here, instead of that, what you can do is probably you can project few columns of R, then take a join of that with S. So you have a table with say 25 columns. Say R is a table with 25 columns, but in the query that you are targeting, only name and roll number are there. So what I do is I take the projection of name columns, name and roll number, and then I take a Cartesian product with, or then I take the join with the table S. So instead of taking the join of the whole table, you do first a projection operation and then take a join with the other table. So that is actually called semi-join. It is a very important operator. So it is widely used in distributed databases, as all of you are aware. So here an example is shown. Here you have an employee table and here you have another table called dependent table, and they are at two different locations. One is at Hyderabad and the other is at say Vijayawada. So two different cities in Andhra. And you would try to take a semi-join. So here, when you are taking a join, all the employee data are to be transferred here, or all the dependent data should be transferred to the place of employee. So instead of that, if you do a semi-join, only few columns of employee need to be sent to dependent So that is actually semi-join. So here you are talking about projecting one particular column. So from the dependent table, you are just executing a query that select all employee dependents names where the age is greater than 71, and then project the SSN alone, and that will be transferred to the node of employees where you take the join of that. That is, you are projecting only the SSN, and that alone is transmitted to employee location, and then you take the join. So what you get is actually the join of employees and dependents, where you have the employee, SSN followed by the name of the employee. So this contains the names of all employees who have their dependents having age greater than 71. So the query is to find out the names and SSNs of all employees who have their dependents age or aged above 71. So let us see the different phases of taking a semi-join. So this is very important. So just go through that. What are the different steps in taking the semi-join operation? The 3 different steps are shown here. So first step is to do an initial local processing where the selection, projections, etc. are applied on the table. Then the semi-join processing, or it is also called the semi-join program, that is derived from the remaining join operations and executed to reduce the size of the relation in a cost-effective way. And the third step is final processing, that is all relations involved are transmitted to the final site and all joins are performed there. That we will see with an example in the next slide. So here let us see that there are 2 tables, R1AB and R2AC. They are at 2 different nodes of a computer network. And now you want to take a semi-join of R1 and R2. So what you are doing is first project the column A, the common column of R1 and R2 is projected, and that alone is sent to the site of R2. So instead of sending, here we are illustrating, or this diagram is illustrated with smaller tables, 2 columns and 3 rows, but actually it can be a huge table. So instead of sending the huge table to the other place, what you are doing is sending only the common column to the other side. All right, and take a join there. Take a join with the table there. So what it is actually 3, 7. So the common, only 3 is common. So the semi-join, what is happening is you take the join of the common column, that is a common column of R and S, R1 and R2 are applied for a natural join with R2. So the result is 3, 7, and that is actually transferred to another location from where the query is coming, and here you send the tuple 3, 6, and the result will be 3, 6, 7. So instead of transferring the whole table, you are transmitting only the most relevant tuples. So that is again illustrated here with another example, a 2-way semi-join. So here you have tables AB and AC. So first the common column is projected, and then you partition it in 2 columns, the R1A, where you have the common column coming here, and you reduce it to 3, 7. Okay. Then shift that alone to 3 alone is shifted to the site 1. Then you take the join here. So what you get is 3, 6, and that is actually transmitted to the site from where the query is coming, and 3, 7 is transmitted here. So here you take the join. So you get the final result. So that is actually two-way join. So there is a join taking place at the site of R2, and there is another join, semi-join happening at the site of site S1, and then finally you merge these two and you get the actual result that you are looking for. So that is actually called two-way semi-join. Okay. So you can just see the different steps described here. All right. So a semi-join, a semi-join from R1 to Rj on attribute A can be denoted by this particular symbol, Rj semi-join Ri. So this portion is open. So if it is closed, it is full join, and if this portion is open, it is called semi-join. So you are taking the semi-join of Rj and Ri, and it is used to reduce the data transmission cost. All right, so the computing steps are: first project Ri on attribute A and ship this projection to from that site of Ri to site of Rj, then reduce Rj to Rj dash. You get a result, a small relation as output of semi-join in that site by eliminating tuples where attribute A are not matching to any value in R1A, RIA. So you get a smaller table as an output there. All right. Then you are proceeding further. So we have seen the second example. So here again it is a So you are projecting the common column to the other side. Then you take a join here. That is the common column with this table. So what you get is actually the resulting tuple. A small relation R2 dash, and that is shipped to the query side, and is 3, 6. That alone is transmitted to matching tuple alone is transmitted to this side, and here you take the join. Now two-way join, an extended version of the semi-join, where a two-way join, semi-join T of Ri and Rj on attribute can be denoted like this. First send the common column to Ri, and then it is sent to Rj. So we have seen it with an example. The steps are: send Ri, the column A, which is common column, from site I to site j, then reduce Rj to Rj dash by eliminating tuples whose attribute A are not matching to any attribute of Ria, and at the same time partition Ria to Ri to Rim, match one of Rja and the remaining columns. So send the minimum of this back to the site of I and reduce Ri to Ri dash. Then using those values, you go for the next phase of the evaluation. So you can actually calculate the cost of evaluation, or you can find out the cost by way of counting the number of tuples which are transmitted from one site to another site. All right. So in this way, you can say what will be the actual cost if it is executed in the normal way, and if it is executed using two different semi-joins. So what is happening is R join S is executed as R semi-join S, full join S. Or you can execute R semi-join, R join S as yes, semi-join or full join or. So the join operator is done in two different steps, first with a semi-join and then with a full join. So we will see this in detail in the next class. I will have a few more examples, and this is a very important operator, important variation of the join operator. So we can see this in detail with some operators in the next class. And also we will see the other forms of the join operator called outer join, where again you have three variations: left outer join, right outer join, and full outer join. All right. Any questions so far? Okay, so on the next class, we will continue with our discussions on this theta, semi-join. It's a very important